Dear students, in this lecture, I would like to discuss about Maxwell's equations inside a material medium. In our earlier lecture, we have considered the derivation of Maxwell's equations for a free medium or free space medium, and also Maxwell's equation for a source-free region. Now, in the case of a material medium, we can see that there is another additional current terms and additional source terms, charge terms are coming due to polarization and magnetization. So, when we use Maxwell's equations inside a material medium, we have to take into consideration the bound currents and bound charges produced due to magnetization and polarization process. Let us start with Maxwell's equations for free space. And for free space, we have the four equations that we have already derived. From Gauss law, we have del dot E is equal to rho by epsilon 0. From Faraday's law, we have del cross E is equal to minus dou B by dou T. And Gauss law for magnetism, that is del dot B is equal to 0. And Ampere-Maxwell relation, that is del cross B is equal to mu 0 J plus epsilon 0 dou E by dou T. In these equations, there are source terms in Gauss flux theorem or Gauss's law and Ampere-Maxwell equation. Now the source term in Gauss's law, that is del dot E is equal to rho by epsilon 0 is rho. Actually this rho is rho F, that is free charges present. That is, we are considering the effect of free charge. Similarly, in the case of Ampere-Maxwell law, there is J. Actually this J is Jf, that is free charge due to actual movement of charge carriers. Similarly, one more term we have, current term is here, that is called the displacement current Jd. So this displacement current is due to change in electric field. Now in the case of a material medium, along with this free charge rho F and the conduction current Jf along with the Jd, that is the displacement current, we need to consider polarization bound charge rho B and currents related to magnetization bound current and current due to polarization, that is polarization current. So we know that polarization is a process by which the positive and negative parts of a nucleus or a molecule separates out in an external field. So in the case of a homogeneous medium, we can see that the dipole moment produced inside the region, or the charges produced or the separated charges inside cancels out, but there is a accumulation of positive and negative charge on both sides of the material used for the polarization process. And we can see that these charges are bound charges. It is not possible to take these charges away from the material as with the case of a free charge. So it is bound charge. So in the case of Gauss flux theorem, we already discussed or already considered about the free charges, but the effect of this bound charge also is to be incorporated in the case of a material medium. And similarly, in the case of Ampere-Maxwell equation, we have already considered two cases, two current terms. One is the conduction current term and the other is the displacement current term. But there are two more current terms are coming. One is due to polarization effect and the other is due to magnetization effect. That is, for polarization, during the process of polarization, we can see that the charges are displacing here and there or slightly adjusting. So that is actually a charge movement, and that produces a current called polarization current. Similarly, during the process of magnetization, we can see that the dipoles, that is the spinning dipoles, orbiting dipoles and spinning dipoles, aligns themselves in accordance with the external magnetizing field. So that also produces a movement of charges, or that is another current called magnetization current. So we need to consider the effect of these two currents also while discussing the Ampere-Maxwell equation in the case of a material medium. Before going into more details about the modifications in the case of a material medium. I think little more discussion is needed related to the current term associated with the polarization. The bound charge rho b is equal to minus del dot p, that equation, and the bound current due to magnetization, that is JB is equal to del cross M, are quite familiar to us. But this term, that is the current term due to polarization, that we are introducing for the first time. So we need to consider the physical meaning of this particular current term. So for that, let us consider a small section of a dielectric, polarized dielectric. And suppose it is a linear material, that is a uniformly polarized material, so that some charge accumulates on both sides of the material. That is, inside there is no accumulation, only on the sides there are charge accumulation, plus and minus charge accumulation. And during the process of that polarization, we can see that there is current is coming into action, and that current is called the polarization current, JP. So let this be the section of the dielectric polarized with the polarization vector P, and the charges accumulated on this side is negative, and the other side it is taken as positive charge on one side and negative on the other side. dA perpendicular is the surface area of the polarized cylinder, and we can see that the current associated with this polarization process may be represented as dI. dI is equal to d by dt of the charge. Charge in this case is sigma b dA perpendicular. Sigma b dA perpendicular, that is the total charges moving to the sides of the dielectrics. That is the total charge. So sigma b dA perpendicular. And we know that sigma b is equal to P. Sigma b is equal to P dot n. As using that equation here, we can see that di is equal to dP by dt into dA perpendicular. Now taking this dA perpendicular to the left side, that is di by dA perpendicular, or it is equal to dP by dt, and that is Jp, the polarization current. Jp is given by dou P by dou T. And also it is possible to show that this the polarization current agrees the equation of the equation of continuity. That is, if you take the divergence, del dot Jp is equal to del dot dou P by dou T, that is dou by dou T of del dot P, and del dot P is equal to rho B minus rho B, so it is equal to minus dou by dou T of rho B. So it is the equation of continuity. Okay. So let us consider the four equations, Maxwell's equations, and what is the modification needed for a material medium. The first equation is del dot E is equal to rho by epsilon 0, and we know that there is a source term is coming. So we need some modification for this equation by including the effect of bound charge also. Now in presence of a dielectric material, we have to rewrite this rho term by rho f plus rho b, that is free charge plus bound charge, and also bound charge rho b is given by minus del dot p. So rho is equal to rho f minus del dot p. So correspondingly the equation changes to del dot E is equal to rho by epsilon 0 changes to del dot E is equal to 1 by epsilon 0 into rho f plus rho b. Now substituting for rho b, this equation becomes del dot E is equal to 1 by epsilon 0 rho f minus del dot p. Now taking epsilon 0 to the left side, del dot epsilon 0 E is equal to rho f minus del dot p. Now take this del dot p term also to the left side, so that the left hand side becomes del dot epsilon 0 E plus p is equal to the free charge rho f. And we are defining the epsilon 0 E plus p. We know that it is nothing but the electric flux density vector d. d is equal to epsilon 0 E plus p. So this equation changes to del dot d is equal to rho f. Del dot d is equal to rho f, and the integral form is surface integral d dot ds is equal to volume integral rho f dv. So this is the modified form of Maxwell's first equation, that is Gauss flux theorem, in the case of a material medium. In the case of free space, we have del dot E is equal to rho by epsilon 0. So the epsilon 0, that is the effect of the material medium, is included inside the vector D as epsilon 0 E plus P, the polarization vector P. The second equation, del dot B is equal to 0 over surface integral P dot ds is equal to 0. We can see that there is no source term coming in this equation. So there is no change inside a material medium. So this equation remains as such for a material medium also, since there are no source terms in the form of bound charges or bound currents present. So no need of any change in this equation. So a material medium also, the equation remains as such. Similarly is the case with the other equation also, that is the third equation, the curl equation, del cross E is equal to minus dou B by dou T, or closed line integral E dot dl is equal to minus surface integral dou B by dou T dot ds. Now in this equation also there is no source term present, so no change for this equation also in presence of a material medium. So the changes needed is for the first equation and last equation. So let us examine what is the change needed for the next equation. That is del cross B is equal to mu 0 j plus epsilon 0 dou E by dou T, and the integral form is mu 0 surface integral j plus epsilon 0 dou E by dou T dot ds. Now we have already two current terms here, that is the free current term is here, and also the displacement current term is here. Now the other current terms we need to include in this source section, that is in presence of a dielectric material, the value of J. We can write it as JF plus JB plus JP. Okay, so along with this epsilon 0 dou E by dou T, this is already there, but we are rewriting this J vector, that is the current density vector J is free current JF plus bound current due to magnetization and the current due to polarization, that is JF plus del cross M. Del cross M is the bound current due to magnetization, and dou P by dou T, that is the current due to polarization. So including these terms, the equation changes to del cross B is equal to mu 0 into J plus epsilon 0 dou E by dou T changes to mu 0 JF plus del cross M plus dou P by dou T plus the usual displacement current equation epsilon 0 dou E by dou T. So additionally two terms we are writing here, that is del cross M and dou P by dou T. Now bringing the mu 0 term to the left hand side, this equation becomes del cross B by mu 0, and also we are taking this del cross M term to the left hand side, that is del cross B by mu 0 minus del cross M is equal to JF plus dou P by dou T, JF plus dou P by dou T plus epsilon 0 dou E by dou T. Or taking the curl outside, the left hand side becomes del cross B by mu 0 minus M is equal to JF plus, we are putting epsilon 0 and P inside the dou by dou T term, epsilon 0 plus P, so dou by dou T of epsilon 0 E plus P, and we know that this terms epsilon 0 E plus P is D, the electric flux density vector D, and B by mu 0 minus M is the magnetic field intensity vector H. So substitute these things here. So the modified equation takes the form del cross H is equal to JF plus dou D by dou T, or the integral equation line integral H dot dl is equal to surface integral JF plus dou D by dou T dot ds. So this is the integral form of the modified equation and the differential form of the modified equation of Maxwell's equation, that is curl equation, del cross H is equal to Jf plus dou d by dou t, that is for a material medium. So the four equations inside the material medium may be listed like this: del dot D is equal to rho f, del dot B is equal to 0, del cross E is equal to minus dou B by dou T, del cross H is equal to Jf plus dou D by dou T. So these are the four Maxwell's equations that we need to use in the case of a material medium. Then the other associated equations are also, that is, these equations, we are familiar with this equation, that is P is equal to epsilon 0 chi E into E, and M is equal to chi M into H, that is the magnetization and polarization related to the susceptibility terms: electrical susceptibility chi E, magnetic susceptibility chi M. So these equations are also correct in the case of a material medium. The other equations are also listed in this, that is the relation connecting D and E. D is equal to epsilon E or epsilon 0 E plus P. That may be written in this form also, epsilon E. Similarly, H is equal to V by mu or V by mu 0 minus M. So these equations are also possible to use in the case of a material medium. Okay, so we have discussed about the modifications needed for the case of a material medium while discussing about or while using Maxwell's equations. The major modifications needed are to incorporate the effect of bound charges and bound currents, bound charge produced due to polarization, and bound currents produced due to polarization and magnetization. So accordingly, we need to modify the equations, two equations with the source terms, that is the Gauss-Flux theorem and Ampere-Maxwell equations. And the other two equations, the curl equation for E, del cross E is equal to minus dou B by dou T, and the divergence equation for B, that is del dot P is equal to 0, remains as such. No change needed for these equations. Okay. That's all for this lecture. Thank you.